Hey guys, Mr. Gucci here, and I'm going to cover the 3.2 notes today, the differences between atoms. Okay, this is our second unit, and there's only three sections in this unit, so we only have one more after this. Let's go. Okay, so this thing is so slow starting up. Always, this computer, you disappoint me. Come on, come on, come on. Okay, cool. The differences between atoms. Okay, so any two atoms of the same element have to have the same number of protons. Okay, their protons have to be identical. That's what makes them a particular atom. For example, every single carbon atom must have the same number of protons. They must have six because carbon is element number six, atomic number six on the periodic table. But atoms of the same element can have different electrons, and they can even have different numbers of neutrons. Okay, so these things can vary. So this section is going to talk about how the electrons vary and what the result is, and how the neutrons can vary and what the result is. Okay, so first of all, atoms of the same element can have different numbers of electrons. These are called ions. An ion is any atom that has gained or lost electrons, and so it no longer has a neutral charge. Okay, ions come in two general varieties. Okay, if you lose electrons, well, now you have more protons than electrons. That means you're going to be positive, and that makes you a cation. That's the name of a positive ion, a cation. Remember, electrons are negative. So if you lose your negativity, you become more positive. On the other hand, if you gain electrons, you now have more electrons than you do protons. You are now a negative ion, and you are called an anion. Okay, if you gain negativity, all right, if you gain electrons, then you've gained negativity. You are an anion, cation and anion. Not cation and anion, cation and anion. Okay? Now, the way I remember this is cat ions are positive because cats are positive, and anions are negative because ants are negative. Okay, that's how I remember it. Maybe you don't like cats and you like ants. Maybe you're a freak. I don't know. But cats are positive, ants are negative. Okay, ions behave chemically different than their neutral atoms. For example, as I've demonstrated before in this class, if you put sodium atoms into water, they explode. Sodium, pure, uncharged, neutral sodium atoms are explosive in water. Chlorine atoms, uncharged, neutral chlorine atoms, are extremely toxic. But if you combine sodium ions and chlorine ions, what you get is just table salt. Okay, so again, neutral sodium, extremely dangerous. Neutral chlorine, it was used as a gaseous weapon in World War I, extremely dangerous. But combine two of their ions together, and you get table salt, which I guess technically has killed more people than either of these other two combined due to issues with like high blood pressure and heart attacks and stuff. So lay off of the sodium, guys. Lay off of the sodium, okay? So oftentimes when we write ions, we just leave off the other information of the atomic symbol. So oftentimes if we wanted to write about a sodium ion, a +1 sodium ion, we'd leave off the atomic number, we'd leave off the mass, and we'll just write the charge. Or a 2 minus oxygen atom, when we're writing the atom, oftentimes, or the ion, oftentimes we'll just write the charge, and usually we'll just leave off the atomic number and mass number when we're talking about ions and how they behave chemically. Okay. Now, the other way I mentioned that atoms can differ is if they have a different number of neutrons. These are called isotopes. Okay. Isotopes are two atoms that have the same protons, so they're the same element, but their number of neutrons is different. Okay. So they'll be the same element, but they will have a different mass number. So down here I got pictures of three atoms of the same element. These are all hydrogen because they each have a single proton. And you can have a hydrogen with one proton and no neutrons. You can have a hydrogen with one proton and one neutron. You can even sometimes have a hydrogen with 1 proton and 2 neutrons. These are all hydrogen because they all have a single proton, atomic number 1, but they're isotopes of each other because they have different amounts of neutrons, and so they have a different mass. All right, this first one is going to have a mass of just 1, okay? 1 proton. This guy's going to have a mass of 2, a proton plus a neutron. This one's going to have a mass of 3, a proton and 2 neutrons. Okay? How we identify different isotopes of the same element is using something called hyphen notation. Okay, hyphen notation. We identify isotopes by their mass number. So here are 3 isotopes of carbon. Okay, this first carbon right here has 6 protons because it's carbon and 6 neutrons, and so its mass is 12 AMU, and so we'd call this isotope carbon 12 or C12. This right here, this version of carbon, is has 6 protons and 7 neutrons. So we would call this carbon 13 because it has a mass number of 13. 6 and 7, that's 13. So carbon 13 or just C13. This last isotope of carbon is carbon 14, which you might have heard of before. It's a carbon with 6 protons and 8 neutrons. All right, so we call it carbon 14 because it has a mass of 14, or C14. Okay, now these are the ways that we would identify isotopes of the same element. Okay, now some isotopes are more stable than others. You might recall that in the previous section we talked about how the job of the neutron is to keep the nucleus of the atom stable. Little positive protons in there are trying to repel each other because they're all positive charged, and like charges repel. But if you can put some little neutron spacers in there, well, then the positive protons can stick to the neutrons. But too many protons, all right, and the atom flies apart. Too many neutrons, and there's not enough positive force to stick everything together. So there's like a Goldilocks zone of neutrons that make an atom stable. So for example, this first atom right here, hydrogen 1, all right, because it has just a single proton, it's stable. Hydrogen 2, because it's got a proton and a neutron, mass of 2, it is also stable. But hydrogen 3, with a proton and 2 neutrons, so 1, 2, 3, that is unstable. It breaks down over time. It is radioactive. And by the way, people will harness these radioactive, unstable elements and extract energy from them. All right? A hydrogen bomb is a bomb that's fueled by these unstable isotopes of hydrogen. It's just filled with a little tank of H3, and under the right conditions, the nucleus will break down, and a nuclear reaction happens, and you can like level an entire city and outlying suburbs. Okay, this is a chart right here that lays out different elements and their stable and unstable version. If it's green, it's a version of that atom that is stable. If it's yellow, then like it's a bit unstable. Maybe it breaks down in a few days. Maybe it breaks down in a few billion years, but it's unstable. And if it's red, it is incredibly unstable. It will break down in a fraction of a second. Okay, so you'll notice some things like hydrogen have 2 stable isotopes. So does helium. So does lithium. Beryllium only has 1 stable isotope and a kind of stable isotope. Oxygen has 3 stable isotopes. All right. Sulfur up here has 3 stable isotopes and a kind of sort of stable one. The bigger the atoms get in general, the more stable isotopes they have. Something like mercury, all right, which has 80 protons, it has like 6 stable isotopes. Okay, so some atoms will have more stable isotopes, some will have less. Every atom has at least 1, sometimes 2. Okay, usually at least 2. Okay, here's a bigger chart of all the known elements. All the little black dots represent a stable combination of protons and neutrons. All the red dots represent an unstable combination that takes hundreds or billions of years to break down. The yellow dots represent unstable combinations that might take days or years to break down. Green and blue, these things will break down in anywhere between days and fractions of a second. Okay, so this is all the stable isotopes of different atoms, right? I think it's a pretty cool chart right there. Now, we can separate out these isotopes using something called the centrifuge, all right? The way it works is simple. A heavier version of an atom that has just like 1 or 2 extra neutrons, is going to be more dense than other isotopes. And because it's more dense, you know, it sinks. All right. Just like if you like layered like oil and water and stuff, the more dense things sinks. Right? Put something dense in water, it sinks. But these atoms are not that much different from each other density wise. So what they do is to emphasize the ability to make it easier for them to sink, they spin them up really, really fast. Really, 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 really fast. All right. Tens of thousands of spins per second, right? Super duper fast. And the heaviest elements, the heaviest isotopes, will migrate to the outside. They will sink to the outside, or they can be extracted. All right. Down here, this hallway of like long tubes. These tubes are spinning on the inside, and they are separating out the heavier isotopes of uranium from the lighter isotopes of uranium. And it just gets respun down the line, getting more and more pure, till at the end of the line, you have pure uranium-235, which is the radioactive uranium they use to do power plants and your basic nuclear bombs. All right? Chernobyl, you ever watch that miniseries? That was uranium. We went to war with Iraq because we suspected Saddam Hussein was building uranium refineries, so ordered a bunch of aluminum tubes to build this kind of uranium refinery right here to presumably make weapons. All right, we sabotaged the uranium centrifuges used by Iran. Okay, because we didn't want them making uranium. They said it was for power plants. We thought it might be for nuclear weapons. He said, she said. So we just destroyed all their nuclear reactor centrifuges. All right, true story. It's interesting. We actually created a computer virus that would sabotage Iranian centrifuges and prevent them from making purified uranium-235, all right, and actually broke them. But we didn't know how we would get this virus specifically just into Iranian centrifuges. So the easiest solution was to just give every computer on Earth the virus and hope that it would be caught by these computers in Iran. And it worked. It's a wild story, okay? So this is how we separate out different isotopes of different elements, all right? Cool. All right? Now, these isotopes don't appear in the same amounts, okay? For example, those carbon isotopes I was talking about before, like 99% of carbon is carbon-12, 6 protons, 6 neutrons. Like 1% is carbon-13, 6 neutrons, 7 neutrons, and like 0.00000000001% is carbon-14. Basically nothing is carbon-14. Like 1 in 10 million atoms of carbon is a carbon-14 atom. Same with lithium, all right? Lithium-6, all right, with 3 protons and 3 neutrons, only like 7.4% of lithium is that version, that isotope. The vast majority of lithium is lithium-7, okay? So lithium is mostly lithium-7. Now, these percents, of course, they will always add up to 100, and rarely is it an equal breakdown. And that makes things hard, okay? Because, like, let's say you're a scientist, and you want to figure out how much lithium to add to a chemical reaction. Well, ultimately, figuring out how much of an element or a compound to add to a chemical reaction, you need to know how heavy the atoms are. So if I'm using a chemical reaction with lithium, am I calculating based on lithium with 3 protons and 3 neutrons, a mass of 6 AMU, or 3 protons and 4 neutrons, a mass of 7? You might be like, Mr. Gucci, well, it's mostly 7, so let's just use 7. But there's some of it's 6, all right? Scientists found a way to account for this using what's called a weighted average. And it's the same way that we tabulate your grade, all right? Let's say you get a 90 in the test category, and you get an 80 in the homework category, okay? In order to tabulate your final grade, we don't just take the average of 90 and 80 and say you get an 85. You know that's not right because your test grades are worth more. Your test grades are worth more than your homework. We take a weighted average, okay, where we multiply your test score by the percent weight it is, in your case 70, and we multiply your homework grade by its weight, 30. and then we add them together, and that is your final grade. Okay? We do the exact same thing here with something called an atomic mass calculation. All right? Where we take the mass of one isotope of an atom and multiply it by how common it is, its percent. Then we take the mass of the second isotope multiplied by its percent, and the third isotope times its percent. All right, as many isotopes as there are, 2, 3, 4, 6, 8, however many isotopes there are, we take their mass and we multiply them by their percent, and then we add them all together. Okay, this is called the atomic mass calculation. Okay? This is the exact same way that we tabulate your school grade. All right, so instead of mass, it's your grade in your test category, your grade in your homework category, your grade in your citizenship category, multiplied by what it's worth. In previous years, tests were worth 50%, homework was worth 20%, labs were worth 20, and citizenship was worth 10. We've streamlined it this year, but we'd have 4 categories. Multiply your grade in that category by its percent and add it all together. That's your final grade for the year. In a time before Skyward, us students, we had to calculate it ourselves in class. All right, we had to calculate it ourselves, and that was annoying. But also, it's like it was really funny for math teachers to be like, "Oh, Jimmy, you sucked at math all year. Now you're trying to calculate your grade, and you're a genius at it. That's hilarious." All right, but it wasn't hilarious, Jimmy. It wasn't hilarious at all. Okay, so I run through some sample problems today in class. I'm not going to run through them in this video. You can just watch the homework and where I run through like 3 or 4 of these sample problems, okay? Now, common misconception here, all right, the atomic mass, that is what appears on the periodic table, all right? And every element on every periodic table, almost, you will see pretty much 2 numbers. Its atomic number, which is how many protons it has, and its atomic mass. Its weighted average mass of all of the atoms that make it up. Okay, remember, the atomic mass is the average of all the atoms. The mass number is just the number of protons and neutrons in one atom. Okay, so atomic mass is the average of all the atoms. That's what appears on the periodic table. The mass number is the number of protons and neutrons in one atom. Take a look at that carbon right there, all right? Do you see the atomic mass is 12.011? That's because, like I said, 99% of carbon is carbon-12, but like 1% of it is carbon-13. And so that's enough to pull up the average by just a little bit over 12. Neon here, the majority of it is neon 20. But there's a little bit that's neon 21. I think even less that's neon 22. And that's enough, once again, to pull up the average just a bit. All right? Just like, if you're calculating your grade and you got like an 89 in your test grade, an 89 in your homework grade, 89 in your lab grade, all right? Well, all that's left is citizenship, all right? Your citizenship could maybe just move it up just a little. Your citizenship is just like 10% it used to be. So it could only move the dial a little bit, okay? Now, because it's an average, if you're doing this right, and I go over it in the homework, if you're doing it right, your atomic mass will always fall between your lowest mass and your highest mass. And it's going to be closest to whatever isotope is most abundant. So carbon, all right, there's carbon 12, 13, and 14. Your atomic mass is going to fall in between 12 and 14, and it's closest to 12 because 12 is most common. Just like with neon, there's neon 20, 21, and 22. But the majority of neon, the vast majority, is neon 20. So your answer is going to be closest to 20. As you do the homework and watch the homework video, if your answer falls outside of the range of masses that you plugged in, it's wrong. In the same way that if you got B's and C's in all of your grade categories for my class, you know you're not going to get a D, and you know you're not going to get an A. All right? If all your grade categories are between B's and C's, your final grade's going to be somewhere between a B and a C, and it's going to be closer to whatever the most important grade category was. Okay? So that's the notes, guys. That is the notes. All right? And good luck. I'm going to upload this, and I wish you all well. Have a good Video. Turn off. Turn off video. Turn off video.